So there's some really important challenges that we had to look at here. First of all, is the AIS signal strong enough to be received from space? With the orientation of the antennas on the ships, generally they're oriented to transmit not this way, but this way. And the ships also pitch and roll with the sea swells. So how consistent was that signal going to be from space? And how big an antenna would you have to have in space to be able to receive those things? So would you need a massive satellite with tons of power and lots of real estate, or could you do it with a smaller satellite? And from space, you're going to see a lot of these individual 40 nautical mile cells all at the same time. So even though in each cell the signals are organized, the communications are organized, when you're looking at multiple cells all at the same time, they're not going to be organized. So you're going to be hearing a lot of transmissions all at the same time. So the challenge was, is there some way to sort of untangle all those signals, because they're all colliding with each other from the orbital perspective? What can you do? Can you actually decode that? Can you identify individual ships? And what's the probability of being able to detect a reasonable number of those? So, actually even before the group was formed in 2005, we started some R&D on this and developed some high fidelity simulators which simulate the ship transmitting the signal and a satellite in orbit and all the various parameters that contribute to that. So the pitch and roll of the ship, the atmospheric attenuation on the signal, the antenna characteristics on the spacecraft, and we started modeling all of this stuff and trying to determine what is the likelihood that we could actually receive these signals. And then we started looking at what can we do to untangle all these collided messages. So got some pretty good results, some pretty encouraging results from some simulation. So then we started doing some testing on the ground using an algorithm that we had developed to be able to untangle a bunch of these signals. So we went to Vancouver and Halifax harbors and sort of went up on the closest, highest hill we could find nearby and tried to receive as many signals from the area as we could. And we were able to show that even at that level, there were some collided signals, because you could see more than one 40 nautical mile cell at one time. And the results we were getting seemed to be encouraging. So we took the next step and we actually did an aircraft-based trial where we collected signals flying at 29,000 feet along the eastern seaboard of the US and around eastern Canada, and then fed those signals in through our algorithm. Seemed to be getting some pretty good results. So the decision was made in late 2007 to embark on a nanosatellite program as a sort of proof of concept for the actual orbital capability. So that's the picture of the satellite there that you can see that we built. And here's some more details about it. It's called NTS. It stands for Nanosatellite Tracking of Ships. And this is a nanosatellite that we developed in conjunction with the University of Toronto's Institute for Aerospace Studies, their space flight laboratory there. And so from initial concept, the first meetings we had with them to say, we want to look at doing this with you guys, to the time that we launched it was 7 months. So you may have heard talk about responsive space or rapid development space. This was a pretty good example of that. So we used a bus design that UTIAS had been working on already. They hadn't built one yet, hadn't flown one yet. They had a bunch of parts that they were getting ready to build one. So we said, hey, you know, why don't you build that for us, and we'll give you a payload, and you can help us find a launch. And that's exactly what we did. So this is a 20 centimeter by 20 centimeter by 20 centimeter cube with a bunch of antennas sticking out of it, about 6.5 kilograms. It's got 24 solar cells on it. We get about 8 watts peak in orbit, and about 3/4 of 1 watt orbital average power. And we designed a payload to be able to operate under those conditions. We've got a very slow S-band link for downlinking of data and uplink of commands, but it worked. We launched it on an Indian PSLV rocket in April of 2008. I was there for the pre-launch campaign. Didn't actually get to stick around to see it go up, but we got it to India, got it tested, got it mounted on the side of the rocket there. You can see it kind of haphazardly hanging off the side of the adapter cone there, but it worked. And here's a map that shows it's kind of a composite image of a bunch of 90-second snapshots that we've done with NTS, starting in mid-2008 until about August of last year. Every one of the yellow dots represents a unique ship that NTS detected. So this was never possible before. With traditional AIS, all you could get was very small bands right along the coastline, and nothing on the rest of the oceans. So this is a world first, and we're pretty proud of it. This satellite was really designed to last no more than 6 months. We thought if we got a month out of it, as long as we could show that we could capture a few AIS signals, we'd be happy. As it turned out, it's still flying. So 3 years later, it's still up there, and really, it's kind of outlived its usefulness, unfortunately, at this point. It's operationally very limited, so there's not a lot you can do with it. Once you kind of prove that the thing works, there's not a lot you can do with it in an operational sense. However, it was used for a few limited operational missions. DRDC Canada had us take some images, capture some data in the Northern Pacific for an illegal fishing monitoring operation they were conducting. It was used off the coast of Vancouver during the Olympics for coastal security. It was used off the coast of South Africa for the World Cup. So it's done some pretty interesting things over its 3-year lifetime. So that's one example. We have nanosatellites, one example of what we call a microspace program. But it's not the only way you can get a payload into orbit. There's a few other ways. One of them is to build a payload and put it on somebody else's spacecraft. And here's an example of that. So we developed an AIS payload for our commercial data services subsidiary company that we call exactEarth, and I'll talk about them a little bit later on. But we built this payload for going on the Indian ResourceSat-2 remote sensing satellite, which was just launched last month. So we had to figure out, okay, how can we build this payload that will interface with this big satellite? It's a big commercial radar satellite, similar to like a radar sat. How can we build something that will interface with their spacecraft? How can we use their communications? Because we can't actually send commands and receive data from this thing directly. We have to use the systems on board ResourceSat-2 to do that. So it was an interesting challenge, and especially when you're working with somebody half a world away and with 10.5 hours time difference. It can be quite a challenge. And just to make it even more challenging, we involved our ComDev Europe division, who actually built the boards and built the uniforms. So interesting program, but like I said,